Hello and welcome to Dunjun. I'm Bill, and this is the series where I'll be documenting and demonstrating the process of making a game from scratch. Today is day 19, and in the previous day I had a brief introduction about Quaternions, what they are, and why we use them for rotations. Please watch that episode before and the one before it on complex numbers, again if you haven't seen that one either. Otherwise this won't make any sense. In the previous episode, yesterday, I taught you what Quaternions were and what they used for 3D rotations in space and how we derived most of the equations. In today's episode, I'm going to be talking about gimbal lock and why we actually use Quaternions over using Euler angles, using Euler's formula to show you how to it's analogous to complex numbers, and doing Quaternion interpolation. So first off, we're going to talk about gimbal lock. Now, gimbal lock, like so, is what happens when you lose a degree of freedom. Now this may sound a bit confusing, but the best way is actually just show you the Wikipedia article. Really, so this is the Wikipedia article here, and I'll make it a bit bigger, about like so. And as you can see as this diagram here, there's like these rotating rings, and each of them attached to a different axis, and these are called gimbals. Now these gimbals will rotate and everything, and each represent a certain angle, like a thing, and these are called the Euler angles. So the Euler angles are your yaw, which is this purpley magenta colour one. You've got your pitch, which will be this green one, and your roll, which will be this blue one. So think of a plane. So as the plane pitches up, it goes up and down. Left to right is your rudders, so that's your yaw, and then your roll is when you tilt your joystick left and right, and it'll roll. It actually roll the thing. But again, the lock is misleading. As it says here, just read this. It tells you a lot about it. But the thing about gimbal lock is this will happen if you had a plane, and if two of these gimbals lie in the same plane, this means that you lose one of the degrees of freedom, and this gets a problem. And the reason for this happening is that there are numerous ways to represent the same angle with using Euler angles. So you could use like 0 degrees or 300 degrees, that's the same thing, or you could use minus pi or plus pi, so it's minus 180 degrees and plus 180 degrees, and they represent the same angle. In Quaternions, this doesn't happen. Only one like Quaternion represents one orientation. Again, there's proper problems here, hard solutions here. For instance, maybe add an extra gimbal. That's what they tried to do on the Apollo 11, and then they try to just say when you get to 85 degrees you stop. Some games actually do this, implement this, when they do like first-person cameras. They actually use Euler angles and then they limit it to about 85 degrees and say we're not going any higher than that on the pitch. And this gets rid of it prevents gimbal lock. But yeah, it's a pretty interesting thing, and this is one of the reasons, and again it says here, using Quaternions. It's a good way of doing it, and this is the reason why we use it mainly. So again, this will tell you why it happens using the rotation matrices, but we're going to explain how to derive the rotation matrices from the Quaternions. So that's the gimbal lock done. So that's all I need to say for that. So the next thing, just get my notes, just reading here. The next thing I was going to talk about is interpolation. Now, I'm going to do this as another title, so interpolation. Now, if you ever heard of interpolation before, the most standard one is called linear interpolation, or LIRP, so linear interpolation. Now this means if you had a point, point A, let's say point 1, and it goes to point 2, anywhere along there you can have any different values, and so this will be your 0th position, and this goes up to your 1 position, So the way you do it is say P prime somewhere along that path. is equal to the initial path plus some parameter, which is that 0 to 1, t in this case, and then the difference of your path, as it says. So this is, you'll compute the difference between p1 and p2. You take the fractional part between there, so between 0 and 1, and then you adjust that initial value of p1 to get the new value p prime. And you can apply this linear interpolation, which we'll be using again in many situations, and we can apply this to quaternions. And the quaternion version of linear interpolation is spherical interpolation, also known as SLURP. They're so brilliant with their naming conventions. So SLURP is spherical linear interpolation. Yes? And the thing about quaternions are, we're not representing points in positions in space, we're representing angles. So that means this difference here is actually the difference in the angular difference, and the angular difference between two quaternions, so the kind of like the angular distance, this isn't actually how you write it, I'm just saying, is actually defined by two quaternions like that. So you got quaternion Q1 and Q2, and then you take the inverse between that. That is the angular difference. This isn't technically correct, don't worry about that, but yes, that's what you do. So first, before we can do that, we need to figure out what this fractional part is. So we've got the difference. Now we need the fractional part t. And now to do that, what we do is going to raise this quaternion by a power, raising it from a value from 0 to 1. So what we're going to do is q to the t, where t is between 0 and 1. So that's what we're doing with quaternion. We're actually raising it to the power. So the general formula for raising any power of thing is q to the t is expressed as an exponential of t times the log of q. And then this begs another question: what is the log of q? Well, first, let's start somewhere else. Let's go back to this famous equation that I showed you again, which is Eulers' formula. Yes? And we did this for complex numbers, where the complex number version was e to the I theta, e equaled cosine theta plus I sine theta. Yes? Now let's do this with a quaternion instead. Instead of using I theta, we're going to use quaternion. So if we do e to the q, this is the same as writing e to another number, and my q here is going to be a pure quaternion. This means it has no scalar part into it, because we're only doing rotations, remember, and rotations will be the pure part. So this is going to be it. So we're going to have that, and then we have a pure quaternion, and it's expressed with an angle. So we have the angle here, and then its axis. And then this, as you guess, is analogous to that, so the I gets replaced with the v hat. And I'm going to make that, so this becomes cosine theta plus v hat sine theta. Very simple. And again, now that means we can calculate what the logarithm of it is. So the log, so now we're going to the logarithm of quaternions. Quaternions, like so. And I've just spelled quaternions wrong. Still wrong. Quaternions. Like this, yes. So if we do log of q, we can express q as this exponential again. So log of q is the same as they'll say in the log, I'm just doing ln for the natural log, of cosine theta plus v prime sine, v hat sine theta. Yeah? Which is again, that's expressed as a nice exponential that we figured out there, yeah? Which was e to the theta hat. And again, anything to that makes it means what we have here is theta v hat, which again is actually just the angle. Isn't that weird? So now we have just done the logarithm. So if we have just a normalized quaternion here, which is expressed as cosine theta plus v sine theta, when you do the logarithm of it, what you get out of it is the angle and the axis multiplied together and become a pure quaternion. So that's pretty interesting. So let's test this, okay? So if we had, let's do the test, and let's do this in green. You know, yellow, yellow. So if t equaled 0, this would mean we get q to the 0, which is the same as me writing as an example e to the log of q. Yeah? Let's just prove it, and we know this is e to the cosine 0. Well, not 0, sorry, 0. Then we've got sine 0 v hat. I'm just doing it on this side here. Cosine of 0 is 1, and the sine of 0 is 0. So this means we've got e to the 1, 0, which is 1, 0. Yeah? So what we've got back is e to the 1, 0 to the 0 is 1, which is true. Anything to the power of 0 equals 1. That's what we've calculated. Yeah, because again we're multiplying that by a 0. We've just still got it there. Yeah, still a 0 on the outside of everything. So it makes it 0. Yeah, good. We know this maths works. So if we set t to equal 1 now, so we've got q to the 1. This is e to the log of q, which is q. So make that sure that's a 1, not just a line. Yeah, that makes the maths correct. So now we're going to move on to the fractional difference of quaternions. And as before, what I expressed was how to do it. So the fractional difference, we can say, is q prime, it's got p prime before, is q prime of 1, the initial rotation, times the initial rotation times that, to the t. So this expresses the difference. So this is your initial rotation, this is your difference, so this is the initial, this is your difference, and that is your fraction along that line, kind of this rotation, yeah? So that's exactly, it's very, very similar to the linear interpolation, but it's slightly modified. However, just wait, this is the problem. This is not the form of spherical linear interpolation that is used mostly. This is technically the correct one, but this isn't what we use. And because it's just too costly, really, because what you've got to do is calculate the inverse, and you've also got to calculate power, which is quite, again, costly. So what we do in general is that the general form for this vector, so the vector of t, yeah, is defined like this. So you've got sine of 1 minus t theta in double brackets, yep, all over sine theta of v1 plus sine t theta of sine theta of v2. So that's what we've done here. So we've got the vector part of the first quaternion, the vector part of the second quaternion. Now if I drew a diagram just to explain this, like I've been doing lately, let's draw that. So we've got a diagram here, a diagram here. Oops, that's not particularly, drew that straight. So let's say, keep with counterclockwise rotations. This here is v1, and let's say that's v2. The spherical bit is we're going round in an arc, and somewhere around this arc is vt. This will be vt, and vt is expressed across that line somewhere, like there. I'll make it that straight line actually. Oops. Like so, like that. So here, along this line here, this v1 here, this is sine of 1 minus t, oops, 1 minus t theta, v1. And along this line here, this is again sine t theta phi 2. And that's what it is. So this formula can be applied to unmodified quaternions. So we change where v is with q. Yeah, so this slurp function now becomes qt equals sine of 1 minus t theta all over sine theta q1 plus sine t theta over sine theta q2. Now that's interesting, and as before I already said, if you can obtain the angle between these two things to be the dot product. So to get the angle, I've already explained this before in the previous episode, cosine theta is equal to the dot product, and it'll give us the angle between. Yeah, works perfectly fine. So what that means is we've got the cosine here. To get the theta bit component, all we have to do is theta now equals the arc cosine of all of that. There, I'm just going to ditto. So that's how we get the theta. Now, again, there is problems with this implementation that we're doing wrong. First, technically the dot product may result in a negative value. And when this happens, the interpolation of it will go the wrong way, and that's not necessarily what we want. And it may sound a bit bizarre. I mean, what do you mean it will go around the wrong way? Well, technically, I haven't even explained this yet. I just realised Quaternions are non-Euclidean, and it's very hard to explain this, but Quaternions are the mapping of directions on a four-dimensional hypersphere. Now that is confusing and is really hard to explain. So if you had a sphere, say it would look like, oops, that wasn't very good, this, yeah, like that. Oh, that was that's a sphere. This is a 2D sphere, yeah. Quaternions kind of represent the mapping of this sphere. So this will be the I and J. And if it was a four-dimensional sphere, you'd have a K component as well. And that's what Quaternions are. They map themselves onto this sphere, on this four-dimensional sphere. So that is pretty much slurp, or the spherical linear interpolation. But there are some other problems arise. For instance, if the angular difference between if the angular distance between these is so small, so like cosine theta is pretty much 1, you may get some floating point errors, and that's not good. Like so. Yeah? Makes sense? Good. So there is also another one called S quad. So quad. Now S quad is called spherical and quadrangle, and this can be used smoothly to interpolate over a path of rotations. So for instance, think about a character and its arm moving and such. That's one way of doing it. So we can have a sequence of quaternions. You can have Q1, Q2, Q3, Q4, dot dot dot, dot dot dot, whatever, Qn minus 1, Qn, like so. Yeah? So we could represent this, and this is very useful, for instance, like arm movements or any skeletal animation, and we want to go between them, and that's one reason why we want to do that. So we can also help define a helper quaternion, which will help us along the way. So let's consider this intermediate point, which I'm going to say is going to be called, I'm just going to think of a letter, let's say M, I haven't made one up, Mi. And this is actually, I'm going to say big exponential function, I'm using exp. And this is equal to the negative of the logarithm qi plus qi plus 1, yeah, times by qi to the negative 1. That shouldn't be dot there, it should just be a times qi inverse plus the log of qi minus 1 qi the inverse all over 4 the qi. And you may have noticed this represents the kind of the curve defined by like a subcurve, or defined from qi minus 1, qi plus 1, and qi plus 2. So this is kind of the base smoothness, and we're actually doing it. It's kind of like, if you've seen cubic curves and everything like that, this is for rotations. And at time t, this thing here can be represented as like squad. So it's called of qi. I'll just put all these functions in. qi plus 1 as the next one. I'm thinking of scalars again, sorry. M, and then mi plus 1, and then t, which is the position. This can be represented as slurp of qi plus 1 of t. And then between the other thing we need to do is slurp between qi, not qi, mi plus 1 of t at 2t of 1 minus t. Oops. 1 minus t. It's a big long equation, I know, it's very confusing, and I'm not going to tell you how to derive it. But these intermediate m quaternions are what we're going to be using. And this squad, again, is very useful. We may not use them at all in our thing. We will be using quaternions for rotations and stuff, and we'll probably not need to use squad because I'm probably not going to do any skeletal animations, but at least you know what they are. And then the last thing I wanted to talk about were the Quaternion-derived rotation matrices. Now again, we all know that matrices can represent a rotation in, we only need 3x3 rotation, but the best way to represent a quaternion is like so. So if I'm just going to write c here every time, and c is going to represent cosine theta. So I'm going to say s is defined as sine theta, which is the angle, and c is going to be cosine theta, because I'm going to be a bit lazy otherwise. This is what I'm going to do. And the other things are, for instance, I'm going to say x is going to be the x-axis, y and z. These are the axes for the thing. Yeah, sorry, I should say vx, vy and vz. So they're the things we're going to be using. So to get our rotation from the quaternion, what we do is c plus a. What am I doing? A? How is that even a letter? A squared minus 1 minus c. Remember, we've probably seen this before when we did the rotations. This is where it comes from. Vx, Vy of 1 minus c minus a. I'm doing the Va again. I'm thinking of axis, not V. So V times S. That's sine Vx, Vz, 1 minus c plus Vys. Go on to the next bit. We have Vy, Vx, and these are just the values, not the actual things. 1 minus c plus Vzs. Then we have c plus Vy squared of 1 minus c. You can see what they're doing on the diagonals, can't you? You got Vy, Vz of 1 minus c plus minus, in this case, and then Vx, s, Vz, Vx, yeah, Vx, 1 minus c, minus in there, v y s, v z, v y of 1 minus c, plus v x s, and the last one, you can guess what it is. It's that. Yeah. So that is the rotation of matrix and how we convert it to a thing. Now you may be thinking, what? Well, as we did before, what we did to get rotate a point P was we had to do this. Yeah? This is how we had to rotate our point to a point of the point. But if we use this matrix, we can do the same thing where P would be our point. This works, but again, the problem is that it's a bit difficult. And also got to remember, this isn't actually cosine theta, technically. It's but in a quaternion it's a bit different, yeah. So that's what we do. So that's quite pretty much all we need to know about quaternions for now. And just to leave you here, any little notes if you want to know stuff, like for instance, nice things to know. So if quaternion can be represented as a scalar and a vector, this is just the end kind of thing, which can be in turn represented as a scalar value plus the vector xi plus vector yi plus vector but vector zk. So that's another thing there. We can also represent it as a length, which we can represent as, say, r, or just q, and then also we can say cosine theta and v hat sine theta. That's one thing we learnt. We can get the angle. So the angle can be extracted either from the scalar part, so that it can be 2 arc cosine of the scalar part, or we can say 2 times the arc sine of the square root of that part, the imaginary part, so vx squared plus vy squared plus vz squared. And again, another way to rewrite that is just 2a arc sine of the magnitude of v. Yeah, that's one way to get the sine. Now, another way to get the axis of rotation, is so the axis of rotation is actually got from the axis, I'm just right here, which can say is that we can get from 1 over sine over half theta of qi qj, not qi qj, it's vi, it's vx, rewrite this again, vx, vy and vz. So that's also rewritten as v prime over sine of that. So I'm going to rewrite that, just remembered, we can rewrite the quaternion. It actually has to be a half theta there. So this is what our quaternion is. So that's all we kind of need to know, and yeah, that should work. So that's all we need to know. That's all quaternions, and in the next episode, please stay tuned for the next episode where I will be implementing quaternions, and I'll show you why I'm implementing in the way that I'm doing. There are a few problems with quaternions, and when we're interfacing with the graphics card. For instance, I've been doing scalar x, y, z. When I'm implementing it, it's going to be x, y, z scalar. It's going to be the opposite way around. And there are reasons for that. I'll explain it when I get to it. So stay tuned for that. It should be a good one, and thank you for listening.